Hello, everyone. Today, our team is presenting our final project on NVIDIA. Our project focuses on using predictive analytics to reduce GPU product returns. Specifically, we are proposing a return risk analytics system that can be built into NVIDIA's order fulfillment process to identify high risk purchases before shipment. To start, I'll give a brief background on NVIDIA and explain why this business process matters. NVIDIA is a global leader in accelerated computing and GPU technology. The company serves several major markets, including gaming, artificial intelligence, and machine learning, enterprise data, enterprise data centers, autonomous systems, and professional visualization. As NVIDIA's products have become more advanced, the product ecosystem has also become more complex. That complexity is valuable because it gives customers more specialized options, but it also creates a higher chance that customers may select the wrong GPU for their needs. That leads directly into the business problem our project is focused on: product returns caused by customer product mismatch. The current GPU fulfillment process is mostly reactive. Once an order is placed, the order is automatically approved and shipped without first assessing whether a customer is likely to return the product. If the customer chose a GPU that does not match their workload, system requirements, or expectations, that issue is usually discovered only after delivery. At that point, NVIDIA has already absorbed fulfillment costs and may also face return shipping, reverse logistics, restocking, product depreciation, and customer dissatisfaction. To understand the size of the issue, we looked at baseline performance across 4 quarters. The baseline data shows that return rates remain consistently high across all 4 quarters. Quarter 1 had a return rate of 18.2%, Quarter 2 increased to 19.5%, Quarter 3 reached 20.1%, and Quarter 4 remained high at 19.8%. These numbers show that this is not just a one-time issue, it is a recurring operational challenge. The estimated return volume also increases as order volume grows, which makes the financial impact even more important. Because of that, our team is proposing a change to the fulfillment process that moves NVIDIA from reactive processing to predictive decision making. Our proposed solution is to add a predictive analytics layer into the GPU order fulfillment workflow. After a customer places an order, the system generates a return risk score between 0 and 1. This score represents the estimated probability that the order will be returned. Instead of treating every order the same, the system separates orders into different pathways. Low-risk orders move through automatic fulfillment. Medium-risk orders receive soft validation prompts, such as compatibility checks or product recommendation reminders. High-risk orders require stronger confirmation of the customer's intended use case and system requirements before shipping. That covers the business problem and the process change. Evan will now explain how the risk score works and how the analytical model supports the new process.
The return risk score is divided into 3 main segments. Low-risk orders fall between 0 and 0.30, and they represent about 62% of orders. These orders continue through automatic fulfillment. Medium-risk orders fall between 0.31 and 0.70 and represent about 28% of orders. These receive soft validation prompts. High-risk orders fall between 0.71 and 1.00 and represent about 10% of orders. These require mandatory intervention before shipment. The key point is that the system does not slow down every customer. Most customers still have a normal buying experience. Now that the risk categories are defined, the next step is explaining how the model produces the score. The analytical enhancement is based on supervised classification. The dependent variable is binary. Return equals 1 and no return equals 0. The model uses historical order data to learn patterns that are associated with product returns. We evaluated multiple candidate models, including logistic regression, boosted decision trees, and neural networks. The final output of the model is not just a yes or no prediction. It is a calibrated return risk score that can be used before fulfillment to guide business decisions. To build that model, NVIDIA would need several categories of data from the order process. The data set would be built at the order level, meaning each record represents a single GPU purchase. Customer data would include return history, purchase frequency, account tenure, and customer segment. Product data would include GPU tenure, GPU tier, VRAM capacity, compute capability, price level, and compatibility complexity. Order data would include order value, discount level, quantity, and timing. Behavioral data would also be important, such as time spent on product pages, engagement with technical documents, product comparison, and cart modification behavior. Once those data sources are collected, feature engineering helps turn the raw data into stronger predictors. Feature engineering improves model performance by creating more meaningful variables from the original data. For example, the system could create a mismatch index that compares the selected GPU to the customer's likely workload. It could also create an engagement depth score based on how much the customer interacted with product pages or technical documents. Other features could include recency-weighted behavior, product complexity scores, and customer return tendencies. Based on our project design, behavioral signals have very high predictive power, while product complexity and customer history are also strong predictors. After defining the data and features, we compared the performance of several machine learning models. The model comparison shows that all three models perform reasonably well, but the neural network has the strongest overall result. Logistic regression has an accuracy of 82% and an AUC of 0.84. The decision tree improves to 85% accuracy and an AUC of 0.87. The neural network performs best with 88% accuracy, 83% precision, 81% recall, and an AUC of 0.91. However, the final selection should not be based on accuracy alone because different prediction errors have different business costs. That is why our project uses a cost-sensitive framework instead of relying only on standard model performance metrics. The cost-sensitive framework is important because not all errors are equal. A true positive means the system correctly identifies and prevents a likely return, creating an estimated savings of $120. A false positive means the system creates an unnecessary intervention, which costs about $15. A false negative is the most expensive error because the system misses a high-risk return, creating an estimated loss of $250. A true negative is neutral because the system correctly allows a non-return order to continue. This framework helps optimize the model around financial impact, not just prediction accuracy. Now that the model and cost framework have been explained, Tim will walk through the expected results, testing plan, and final recommendation.
Thanks, Evan. The financial impact simulation shows the practical value of the predictive system. In a 10,000 order example, the current reactive system results in about 2,000 returns. With the predictive model, return volume drops to about 1,300 returns. That produces an estimated profit improvement of $175,000. The quarterly improvement also shows the value of the model over time. Baseline return rates range from 18.2% to 20.1%. After the model is applied, the post-model return rate drops to 17.9% in quarter one, 15.6% in quarter two, 14.2% in quarter three, and 13.1% in quarter four. Quarter four is especially important because it serves as the holdout test period. These improvements also change how different participants interact with the fulfillment process. The system affects several groups. Customers move from being passive buyers to guided decision partners. Most customers are not interrupted, but higher risk customers receive guidance that can help them avoid buying the wrong product. Operations teams move from reactive return processing to risk-based fulfillment. Sales support become more risk aware and can provide better product guidance. Data science also shifts from traditional reporting to supporting an operational decision engine that directly affects fulfillment. To confirm whether the solution actually works in the real business environment, our team recommends an A/B test. The proposed experiment is a randomized A/B test. The control group would continue using the current reactive fulfillment process. The treatment group would use the predictive risk return score process. The experiment would include 75,000 orders per group for a total of 150,000 orders over a 6-week testing window. Stratified random sampling would be used to balance group across product category, order value, and customer segment. The primary metric would be return rate. Additional metrics would include cost per order, profit per order, conversion rate, and customer satisfaction. The goal is to confirm that the treatment group reduces returns without harming sales or customer experience. the experiment is successful, if the experiment is successful, the next focus is making sure the system can be deployed reasonably and maintained over time. For long-term sustainability, the system needs governance and monitoring. Model expandability is important to shape values, can be used to show how an order was classified as high risk. High value or enterprise orders should include human in-the-loop review. The system should also keep audit logs of model-driven decisions. Threshold calibration is important because too much intervention could hurt conversion rates or customer satisfaction. Finally, the model should be monitored for data drift and concept drift, then retained as customer behavior. GPU products and market demand change. To close, I'll summarize our final recommendation and the overall value of the solution. Our final recommendation is that NVIDIA should implement a predictive return risk score with the GPU fulfillment process. This solution is practical because it can be added as a scoring layer without redesigning the entire fulfillment system. It is useful because it lowers return rates, reduces logistics and depreciation costs, improves product customer fit, and increases profit per order. It is also scalable because the same concept could be applied to other high-performance computing products. Overall, the system transforms GPU fulfillment from a reactive process into a proactive, AI-driven decision intelligence system. That concludes our presentation, and thank you for your time.